All right. Making insoluble salts or precipitation reaction, we also call it salt precipitation. Remember, as soon as we use the word precipitation, the first thing that should come to your mind is that we are talking about an insoluble salt, and we're talking about its preparation. Now, the very basic procedure of it is to mix solutions of two soluble salts, and what we usually get in return is one insoluble salt and one soluble salt. So I'd like to generalize this whole equation. What happens is that you take a soluble salt and you mix it with a soluble salt. As you can see, aqueous over here and aqueous over here. So this should make sense. And you're going to get an insoluble salt, which is pretty clear if you take a look at its state symbol, since that's solid, and you get one soluble salt. Again, remember, this soluble salt is different from the soluble salts that we mix in the first place. It's not going to be same. It's never going to be same. Okay. So that's also aqueous. This gives you the idea. So what is a precipitation reaction? A precipitation reaction is a reaction in which a precipitate is formed. What is a precipitate? A precipitate is a solid that is formed by a chemical reaction. It may also involve liquids or gases. Whenever a precipitate is produced, since it's an insoluble solid, it tends to settle at the bottom if it's heavier. So what happens, as you can see in this test tube, this is a filled test tube. There is liquid all the way in this test tube, and the solid tend to settle. And I'm going to use a different color since that's not much visible. The solid tends to settle down at the bottom of the test tube. So this bottom portion, although we have liquid in these parts as well, but the solid tend to settle down at the bottom because usually the insoluble salts that we form are heavier in density as compared to the liquid that we have. In this specific reaction, silver nitrate is reacting with sodium chloride, it's producing silver chloride and sodium nitrate. Now, out of these two, one of them is soluble, one of them is insoluble. How would you know which one is soluble or which one is insoluble? Actually, that's a prerequisite that comes from the previous part of the book. So I'm going to scroll a little and I'm going to take you to that part of the book which tells you which salts are soluble and which are insoluble. So really, we have a big table on the previous pages. And if you look at those tables, you'll get to see that the salts that are insoluble are completely colored or almost insoluble, have a little bit of gray in them. So if we take a look, then we can really finalize which of these are insoluble and which of these are soluble. Now, if we look at this table, it's a little difficult to remember which ones are soluble or insoluble. But if we go with these points, if we try to memorize these points, it's pretty easy. Now, take a look. All sodium salts, potassium salts, ammonium salts, and nitrate salts are soluble. So that's a pretty easy thing to understand. Now, among chlorides, most of them are soluble, but there are only two exceptions. One, and this is second one. Lead 2 chloride, silver 2 chloride. You're supposed to memorize these names. Now, you just saw we formed silver chloride in the reaction I told you. So from here, from this point, we know that it was supposed to be an insoluble salt. It was supposed to form a precipitate. It was supposed to settle down at the bottom of the test tube. So that was all supposed to happen from this prerequisite knowledge. Not just that, when we talk about sulfates, well, most of them are soluble. Again, we have four exceptions: lead sulfate, barium sulfate, silver sulfate, calcium sulfate. Now, if you take a look at it, you'd know that lead in the form of chloride, lead in the form of, or silver in the form of chloride, or lead in the form of sulfate, or silver in the form of sulfate are insoluble. So we do understand that uh, there are some specific compounds which are insoluble for most of their forms, all right? So all carbonates are insoluble. Just the three carbonates that are soluble are sodium, potassium, and ammonia. Now, this is relative to this point. Since all sodium, potassium, and ammonium compounds were soluble, so their carbonates are also going to be soluble. And if we leave these out, all the carbonates in the world are insoluble. All right. So most metal hydroxides are also insoluble or almost insoluble, except the ones, which ones? Again, sodium, potassium, ammonium hydroxide. Calcium hydroxide is slightly soluble in water. So yeah, if you remember just these three and put the rest into insolubility quotient, you'd understand. So there are two exceptions for chloride, four for sulfate. All of the carbonates are actually insoluble. The exceptions are about the solubility. There are three. For hydroxide, again, all are insoluble. The exceptions are about three. You may add calcium to the list, that's fine. So it's 1, 2, 3, 4, 5, 6. Now there are 1, 2, 3, and then there are 1, 2, 3, 4. So if I look at it, it seems that there are only about 10 to 11 specific compounds that are exceptions you need to remember. And there are two rules on top of it that you need to remember. That's about it. So this entire table can be broken down into separate parts and can be easily memorized. Once you memorize it, only then it's going to be helpful for you to decide in precipitation reactions whether a specific compound is going to form a precipitate or it is going to be soluble. Right? So from here on onwards, every question that we are going to do for this precipitation reaction, I'm going to discuss the same prerequisite knowledge. From here, we are going to know that this silver chloride is insoluble because we studied it as an exception for the chloride. We studied only two, lead chloride and silver chloride, out of which silver chloride is a part of this equation and hence insoluble. And remember, we put this symbol next to the precipitate. It won't dissolve in water. It has a white color. Now, in case of precipitation reaction, different precipitates are going to show you different colors. So we are supposed to remember these as well as visible observation. Now, we need to explain what's happening over here. Now, let me clarify that whatever is happening over here is pretty much very easy to understand because it's a simple exchange. I'm going to explain the whole thing from the equation first, and then I'm going to take help of these diagrams, and both pieces of information are going to conform one another in terms of their understanding. Now, what I'm going to do is that I'm going to break apart this compound into positive and negative ions. Again, this one as well, positive and negative. What are we doing? The negative of this one is combining with the positive of this one and vice versa in the other parts. So it's really easy. To be honest, in precipitation reaction, both the soluble salts actually exchange their ions. The positive of one combines with the negative of second, and the negative of the first one combines with the positive of the second. And that happens in almost all precipitation reactions that are based upon mixing of two solutions. So if you understand positive of one is combining with the negative of the other, and vice versa with the other two ones, so you'll see the same thing over here. Now, take a look. The first salt is composed of big blue and small gray balls. The second one is composed of big green and small black ones. Notice the green ones and the gray ones combine. The big balls of this one, I mean the ions that are bigger are combining with the smaller from this side, and the ions from bigger from this side are combining from the smaller with the other, and that's what is happening. Now, out of these ones, they have drawn the specific precipitate in such a way that you would easily know this belongs to a solid. And an insoluble solid, this is since this salt cannot be broken down when by water and they are not dissolving. Now you see these ones as separate ions. You don't see them combined together in a tight packed lattice in a proper arrangement. Why? Because these ions are soluble. And what solubility means is that they're gonna roam around the whole solution, the whole water thing, as per the please, as per they collide with one another. And that's what soluble salt means. The positive and the negative ions break down from each other and they move around the system as they please. But yeah, we have drawn them separately since they are also spectator ions. These are not the ions we are interested in this reaction. We call them spectator ions. Let me clarify myself from the equation above. Now, if you see this equation, you would know that this is the salt that we are interested in. This is not what we are interested in. So we're gonna both call both of these ions as spectator ions. We're not interested in these. They are just the collateral product. I hope you understand the meaning of collateral product. When I say collateral product, it is the product that is formed because the reaction occurred. We were never interested in this product. All right. So we are only interested in our precipitate. So apart from precipitate, any other ions will be considered as spectator ions. Okay. So what are you supposed to do? Extension work. How are you gonna write all of this? So whenever you see an equation, to work out an ionic equation from a precipitate reaction, consider the solid only. And then consider the ions from the left side for the solid as well. And forget the spectator ions. So if this entire reaction, and I'm going to write the whole reaction since I don't want to scroll the screen every single time. We reacted these, we formed this, along with this, our spectator ions or the collateral product, what I was calling it. All right. So this is it. So for the formation of silver chloride precipitate, actually we needed the silver ion from this side and chloride ion from this side. So in order to write the equation, I'm going to write the silver ion, which was in aqueous form. It combined with the chloride ion in aqueous form, and I'm going to write the proper symbols. They're going to form silver chloride. My bad. This is not P, this is Q, of course, and this is not P either. Oh, sorry, this is G. Q is actually the part of aqueous. What am I doing? So yeah, solid. All right. So that's how we form the ionic equation. What I'm trying to explain is that you do not need to consider spectator ions in the equation, either on the left or on the right. Just combine these ions, form this structure. How would you know their charges? You can depict any one of their charges. Since this one is negative, of course, this is going to be positive to balance out the whole thing. So yeah, Ag positive, Cl negative. For example, in sulfate, barium sulfate is insoluble. So how would you know? You definitely know in case of sulfate that it has a negative 2 charge from the previous portion. So if there are no numbers over here, barium definitely has some balancing charge, and that would be positive 2 only. Let's talk about something else. Lead 2 chloride, another solid. For this, we don't even have the equation. You don't need an entire equation to work this out. So, of course, you have chloride ions and you have lead ions. Now, since you have 2 over here, so you need to balance chloride ions like this. Since chloride only have a negative charge, so we needed to balance it over with a 2 over here. Now, since this 2 must be taken from cross multiplication over here, so lead must be plus 2, so aqueous, aqueous, and solid. And remember, these state symbols always remain the same. Aqueous, aqueous, solid, aqueous, aqueous, solid, and you might be seeing the same thing in every single example from the book or from mine. So I hope this makes sense. I hope you understand it's the solid, it's the precipitate only that we're going to consider for the ionic equation. And I'm trying to talk about the ionic equation as an extension work. And we don't need to worry about the spectator ions, and the book says the same thing. Moving on. Now, what do we mix together to make insoluble salt? That is a big question. All right. For example, I'm gonna again go to the previous page. I'm gonna redo this entire thing. Okay. All right. Now, since you can see that I have formed barium sulfate, so the question is, which two salts are you exactly going to mix to form barium sulfate? Now, you already know that you have barium ions over here, you have sulfate ions over here, and they are forming barium sulfate. In order to complete the equation, you can come up with anything over here as a positive ion, over here as a negative ion, and definitely this is going to form your spectral ion-based substance. Now, remember, the positive ion over here should have a negative ion, and for negative ions, like we have previously studied from the prerequisite, which ions are soluble, which are not, nitrate are the only negative ions that are soluble every single time. So don't think about any other salt. For the positive ions, add nitrate to the system in order to balance the whole thing. This two goes over here, this negative comes over here. What does this become? This whole thing becomes, and I'm going to rewrite it as barium nitrate. Sorry, I need to rewrite this 4 correctly. This is 3, and yeah, this is 2. So every time, no matter which positive ion is here, the negative ion is supposed to be nitrate. So that way, it would always be aqueous. And you're never going to write something wrong. Since remember the prerequisite, all nitrates are soluble. Now, of course, we need a positive ion with the sulfate. Remember, it can either be sodium, all sodium ions are soluble, or potassium ions, compounds, sorry, not ions, compounds are soluble, or ammonium ones are soluble. Since for ammonium, this can be a little bit difficult, so don't pick this one, either pick this one or pick this one. So yeah, you can either pick this one. If the two comes over here, this becomes sodium sulfate. So what's the formula of sodium sulfate? I'm going to erase this, this, and this. It becomes Na2SO4. So either take Na2SO4 or take K2SO4. Why is that? They're going to be aqueous every single time, and you won't make a mistake by writing an insoluble substance on your list, because you cannot start with an insoluble substance. So since you took sodium over here and nitrate over here, every single time you're going to wind up with sodium nitrate aqueous over here. If you're taking potassium over here and nitrate over here, you're going to wind up with potassium nitrate over here. So if you remember this technique, even if they tell you this single name and ask you which two compounds you're going to mix, which two aqueous solutions you're going to mix, you would know. One of them would be a sodium-based solution. One of them is going to be a nitrate-based solution. And that's exactly the same thing the book explains in the very next part. Now, they come up with a salt. Let's say you're supposed to find lead to iodide. Now, lead is a positive ion, iodide is a negative ion. So the negative should be combined with sodium. The positive should be combined with nitrate. So you start with lead to nitrate, which is soluble, and sodium iodide, which is also soluble. You form lead to iodide precipitates, which are pretty yellow color, and you can see the refined yellow color. This is instantly forming upon mixing, and this yellow color is quickly trying to settle down at the bottom. That's our precipitate, and you'll get sodium nitrate solution as set of spectator ions. What is the ionic equation? This one is the ionic equation. So no matter, I do understand for iodides, there was nothing written in your prerequisite part. You never know whether the iodides are soluble or insoluble, or which the iodides are soluble and which ones are insoluble, to be exact. But as soon, even if the examiner comes up with something that is out of that prerequisite table, it shouldn't be a problem. Since you know the technique, since you know that the first part of this becomes a nitrate, the second part of this combines with sodium, and that's how we write the full equation. And we're going to wind up with this ionic equation and with this spectator ion every single time if we use nitrates and sodium. Now, in order to form barium sulfate, now barium is going to combine with nitrate, sulfate is going to combine with sodium. This is the exact example I just used. You may even combine it with potassium. If you do, you're going to end up with potassium nitrate instead of sodium nitrate. Now, barium sulfate is a white precipitate, and try to remember the colors of the precipitates. They're important in your course. It is insoluble in water, so it will settle down at the bottom. And there you go, you have the ionic equation. I told you about this ionic equation on the previous page already. Now, a part of all of these theoretical work, we might need to go with something practically. So if you do, whenever you are about to handle something toxic, for example, sulfates and lead compounds are all toxic, so skin contact must be avoided. So wear protection, whether those are gloves, whether those are eye protections, whatever that is, always be safe. So preparing a pure dry sample of lead to sulfate, we take 25 cubic centimeter solution of lead nitratic in a beaker, and we take similar amount of sodium sulfate. Amounts don't really matter because if anything is in excess or anything is in limiting, we're going to get rid of it later. So a white precipitate of lead to sulfate is going to form. Reaction mixture is filtered. Since the solid is insoluble, in the filtration process, it would become a part of residue on the top of filter paper. Remember, for these kind of reactions, it's pretty easy. This is going to become the residue on the top of the filter paper. This is going to become a part of the filtrate and will pass, the filter paper to move to the beaker at the bottom. I mean, below the filter funnel, of course. So whatever we get on the top of the filter paper, we can wash those crystals and we can dry them. Remember to wash them with distilled water. 20 cubic centimeter portion would be fine enough. You may use 10, you may use 15, you may use a little more than 20. That's fine. So this portion is not important. What's important is to wash away everything that is soluble and just have the insoluble pure salt on the top of the filter paper. Washing can be repeated several times to make sure that the sample is not contaminated. So yeah, wash it once with the 20 cubic centimeter portion, then twice and thrice. So keep on doing that until unless you're sure that you don't have any contaminations left. We then transfer the filter paper to a warm oven to dry it. You can even dry it under the fan. You can dry it under the sun. You can dry it in an oven. It's all up to you. But we suggest that you can do it in an oven since that is a quicker way to do that. Remember, washing is only done with distilled water. You never wash with tap water because tap water is again going to contaminate since tap water has many dissolved substances. So tap water is going to contaminate it with more salts, which is not a good idea. So since we had many methods, remember, if the salt is not soluble, precipitation is the technique that we use at this point. We mix two solutions, and if they contain the correct positive and negative ion, you're gonna wind up having that salt on the top of filter paper as the residue since it's insoluble. That's about it.